Bonjour à tous. Donc on va avoir la chance aujourd'hui d'avoir un séminaire de Fiorenza Fanelli du CNR NANOTEC à Bari en Italie. Donc c'est un séminaire donné au LAPLACE et diffusé en même temps au réseau plasma froid en visio, et les personnes qui continuent à arriver encore côté réseau plasma froid. Et la vidéo sera disponible ensuite sur le site web du réseau plasma froid pour pouvoir la re-regarder en détail et pointer tous les aspects des travaux de Fiorenza.
Merci beaucoup. Bonjour à tous. I'm very pleased to be here and thank you for joining this seminar. Before starting, let me acknowledge Nicolas Naudet for inviting me to visit the LAPLACE laboratory here in Toulouse and to deliver this talk, in which I would like to share with you some of our recent advances in surface engineering of materials by using a dielectric barrier discharge at atmospheric pressure. Before starting, let me add some comments regarding the Institute of Nanotechnology of the Italian National Research Council, in which I have carried out my activities since 2011. Our institute operates through 4 units in central and southern Italy, and I actually work in the Bari unit that is hosted at the Department of Chemistry of the University of Bari. In this sense, we have a very strong collaboration with researchers and professors of the Department of Chemistry of the University of Bari, and the team in which I work is really a joint team between the University of Bari and the Institute of Nanotechnology of CNR. So, which is the main mission of our unit. We mainly focus on plasma science and technology applied to the development of multifunctional or advanced materials and devices. And so there are different groups that focus on the optimization of new plasma processes, and also on some fundamental investigations of the plasma. Our focus and my focus, the focus of my research activity, is mainly the utilization of dielectric barrier discharge at atmospheric pressure for surface functionalization and materials engineering. Of course, as everyone knows here, over the last 2 decades, our community really focused and really intense research efforts have been devoted to atmospheric pressure plasma processes and their application in surface engineering. And of course, this is due to the fact that atmospheric pressure plasma processes combine the key advantages of non-equilibrium plasmas and atmospheric pressure operation. So they really promote unique reactions and interactions in the gas phase, near interfaces, and even in the liquid phase that are otherwise impossible to achieve with conventional methods. On the other hand, from the if we consider the possibility of operating at atmospheric pressure, there are some opportunities that are mainly related to the potential reduction of costs of reactors and processes, the utilization of, let's say, easy to handle apparatuses. But I would like today in particular to point on some unique opportunities offered by the possibility of operating at atmospheric pressure. And in this sense, the atmospheric pressure operation offer the unique opportunity of for processing highly porous or highly outgassing materials, for instance, and also atmospheric pressure plasmas are in principle compatible with aerosols of pure liquid, but also of complex mixtures, such as solutions, dispersions. And this, as we will see today, opens the possibility of depositing, let's say, hybrid and micro nanostructured thin films. So this is just to mention that in Bari we are mainly using dielectric barrier discharges because they are characterized by a simple and versatile design. They are compatible with both direct and remote approaches, and they are, let's say, scalable to large area substrates. For this reason, we mainly focused on the over the last 10 years on the utilization of DBDs. And here is the general outline of my presentation, in which I would like just to focus on two main topics. The first one is the preparation of aerosol-assisted hybrid organic inorganic nanocomposite thin films by using aerosol-assisted plasma processes. And the second part of this talk will be dealing with the surface modification of porous materials. The focus of this talk will be mainly on process optimization. It is on the criteria we used when we optimized for the first time these processes, and that helped us to understand also the potential of these processes. And I will also present some potential applications of plasma treated materials. And let's say the fil rouge of this presentation will be the development of new functional materials for environmental remediation. This is just a choice, just to remain focused on some possible applications. And these particular, in this talk, I will try to enlighten how the wetting properties of the plasma treated materials or other additional functional properties that we are able to impart to the material can be exploited, for instance, in environmental remediation. And let's start with the first part that focused on the aerosol-assisted deposition of organic inorganic nanocomposite layers. So over the last 10 years, several groups in our community have focused their research efforts in the investigation of the combination of aerosols with atmospheric pressure plasmas. One of the main advantages of using aerosol is related to the fact that it is possible, let's say, we are not limited to select low volatility precursors. It is possible to use high volatility, precursors. It is possible then to use thermally unstable or low volatility precursors, and also what we can define unconventional thin film precursors. Let's say it's conventional, at least for the plasma community. And we are, I'm referring now to the use of solutions and nanoparticle dispersions. So the utilization of these precursors can lead to the deposition of nanocomposite thin films, that is multi-component layers that can comprise different phase domains, and which at least one type of the phases has at least one dimension in the nanometer range. And over in the last decade, several groups published papers in our community on the preparation of all inorganic thin films, such as thin films containing TiO2, nano inclusions in, let's say, silica-like matrix or silver nanoparticles in a TiO2-like matrix. And also all inorganic thin films have been prepared. This typically, if for instance, the plasma is fed by, let's say, transport gas and aerosol of a solution, for instance, containing a biomolecule, a dye, and so on, it is possible to obtain, for instance, all organic nanocomposite layers that can contain molecule-loaded nanodomains or other organic domains of other species embedded in a polymer matrix. Of course, there are several examples on the preparation of organic and inorganic nanocomposites, and this is mainly the focus of our work in Bari. Let me briefly describe the strategy we use. In principle, it's a very simple strategy. The DBD is fed by a transport gas and a main gas and the aerosol of a dispersion of preformed inorganic nanoparticles in an organic liquid precursor. This leads to an organic-inorganic nanocomposite layer that consists of inorganic nanoparticles embedded in the organic matrix formed through the plasma polymerization of the solvent of the dispersion. This is one of the possible approaches to obtain organic-inorganic nanocomposite coatings by aerosol-assisted plasma processes. We are using, in our case, in our work, this approach. And what about the versatility and generality of this method? It merely relates to the possibility of combining a wide range of nanoparticles and organic precursors. That is, in principle, the process does not need to fulfill to the requirements to obtain the in situ synthesis of the nanoparticles in the plasma. This is just a possibility, because there are now new approaches in which it's really possible to synthesize the nanoparticles in situ along with the matrix in a single-step plasma process. But for instance, if we need to really embed or immobilize on a surface a specific nanoparticles with a specific structure and shape that cannot be achieved easily by plasma, this can be a solution as far as the nanoparticle is dispersible in the liquid precursor. That is, we need a certain chemical compatibility to obtain a dispersion of good quality, depends from the application, that can be injected in the plasma. And so, but in 2014, we started to investigate the growth and structure of organic and inorganic nanocomposite coatings that deposited by aerosol-assisted plasma processes. We use, of course, a classical parallel plate DBD reactor with a lateral gas injection of the feed mixture in the inter-electrode zone. And we mainly focused on a very simple system, that is a hydrocarbon polymer, metal oxide nanoparticles, nanocomposite coatings. The particles we use are actually zinc oxide and titanium dioxide nanoparticles. And so in our process, a dispersion of only capped zinc oxide or titanium dioxide nanoparticles in a hydrocarbon solvent mixture is injected in aerosol form in the DBD. why aerosol capped this just to achieve a good dispersion and to disperse the metal oxide nanoparticles in haplopolar solvents. And the plasma was operated in a classical filamentary regime, and the main gas in this case was helium or argon, so a noble gas. And the plasma was operated in pulsed mode. And let me show an overview of the typical chemical and morphological properties of the deposited, the coating that we were able to deposit by using this approach. Here you can see, first of all, the classical ATR FTIR spectrum of the coating that shows clearly that the coating combines the typical chemical features of both oleic capped zinc oxide nanoparticles, in this case, and the hydrocarbon polymer formed through the plasma polymerization of the organic solvent. What about the surface chemistry? And it's very important to keep in mind the surface chemistry of this material. The surface chemistry is mainly dominated by the organic component. That is, as you can see, the carbon atomic percentage is almost 90%, while the zinc and of course also oxygen atomic percentages are pretty low. So the surface chemistry is dominated by, in this case, a low surface energy hydrocarbon polymer. What about the zinc oxide nanoparticles? XRD and XPS analysis confirmed that they keep their chemical integrity in the nanocomposite coating. So in principle, we do not change their chemical structure, their composition, and the crystallinity, and so on. Let's move to the morphology. So, as you can see here, the coatings, these coatings are hierarchical micro-nanostructured coatings containing quasi-spherical nanoparticles agglomerates covered and held together by the organic polymer. That is, it seems clear from morphological investigation that the role of the polymer is, the polymer has a twofold role of really holds together the nanoparticles agglomerate in the three-dimensional porous structure of the coating, and it also has a very important role in the adhesion of the coating to the substrate. The formation of quasi-spherical nanoparticle agglomerates is expected in principle, because it is widely reported in the literature on spray drying processes of nanoparticle dispersions, which it has been widely demonstrated that typically the evaporation of the solvent leads to the formation of these micro-nanostructured spherical agglomerates. We also evaluated the possibility of controlling the composition and hopefully the morphology of the nanocomposite coatings deposited in aerosol-assisted plasma deposition processes. There are in principle two strategies. In Bari, we mainly focused on the possibility of changing the chemical composition of the starting dispersion. This is a solution that can offer some possibilities, but it's also very important to act on the electrical parameters of the DBD. And let me add that here in LAPLACE, but also in PROMES, there is the teams here really gave a great contribution in this sense. That is, in the optimization of the electrical parameters of the DBD to improve the transport of the nanoparticles to the surface, or the growth of the organic matrix, or improve the dispersibility of the nanoparticles in the matrix. We mainly focused on the composition of the dispersion, and first of all on the concentration of the zinc oxide nanoparticles in the dispersion. So as you can see here, I reported the zinc oxide loading in the coating. So as you can appreciate, by increasing the zinc oxide nanoparticles concentration in the dispersion from 0.5 to 5% by weight, we obtain a zinc oxide loading in the coating ranging from 25 from 80 percent by weight. This also leads to a considerable increase of the deposition rates. That is, we can really reach thin films with a thickness of even 10 microns with 5-10 minutes of deposition. In such a way, the incorporation of the nanoparticles is really favored in our condition. And as you can appreciate from the SEM images, we can really appreciate the formation of nanostructured thin films, highly porous thin films, with root mean square roughness that can be as high as 1 micron and even greater. There is in principle another way to change the chemical composition of the coatings by acting on the composition of the liquid precursor of our dispersion. For instance, in our work, we used as a mixture of normal octane and 1,7 octadiene. So we try to investigate the influence of the concentration of octadiene in the mixture. Of course, the presence in these molecules of 2 terminal carbon-carbon double bond can really lead to could lead to an enhancement of the growth rate of the organic component. And as you can see, if you look at the zinc oxide loading, at least in our process, we observed that when the concentration of octadiene is really low, it's lower than 2% by volume. In such a way, it seems that this promotes the immobilization of nanoparticle agglomerates in the coating. While if we further increase the concentration of octadiene, we can really observe a decrease of the zinc oxide loading. And as you can appreciate from the SEM image on the left, we have now that the contribution of the organic component is promoted. From transmission electron microscopy investigation, we also had the feeling that if we are able to promote the growth rate of the organic component, we are also able to, in such a way, reduce the contribution from highly packed nanoparticle agglomerates. So it seems that if you are able to manage the growth rate and increase the growth rate of the organic component, we could also in such a way reduce the contribution from highly densely packed nanoparticle agglomerates. Let me focus now on the wettability of the deposited coatings. We know that the presence of these nanoparticles agglomerates in principle for main application can be a real problem. And this is why, for instance, different groups in our community are really trying to improve this aspect. But when we started with this coating at the beginning, okay, we were not so happy of this, the presence of these agglomerates. But looking at let's say, being a little bit out of our box, it's very important. It's very important to keep in mind that the preparation of highly porous thin films can be very important for catalysis, or the preparation of hierarchical micro nanostructured coatings can really lead to super hydrophobic and even super amphiphobic wetting properties. So we try to exploit this, let's say, drawback of our coating, and to evaluate if we were able to obtain easily, that is also with a simple process, reproducible process, and very low deposition time, as low as 1 minute, super hydrophobic coatings. Of course, this is possible. As you can see here, I've summarized the advancing and receding water contact angles of our coating as a function of the zinc oxide loading in the coating. And as you can appreciate that in this case, when the zinc oxide loadings exceed the 65%, we are able to obtain coatings that show an advancing and receding contact angle greater than 150 degrees, and an hysteresis, that is the difference between the advancing and receding contact angle, less than 10 degrees. This means that we obtain low hysteresis, super hydrophobic coatings. The water droplets simply roll off these surfaces. And why we obtain these coatings? Due to the coexistence of a low surface energy conferred by the hydrocarbon polymer that dominates the surface chemistry of our coating, and a hierarchical microscale to nanoscale roughness induced by the nanofiller. We also explore the wettability of our coating, considering a hydrocarbon liquid, and such as hexadecane. And as you can appreciate in this case, we have a super oleophilic wetting behavior. That is, the contact angle for hexadecane in this case is less than 10 degrees. And this, if we look at both water and oil, we can conclude that in this case we obtain super hydrophobic, super oleophilic coatings. That is, we obtain wettability selectivity. That can be exploited in several fields. Let me show you an example related to the preparation of filtration materials for the separation of immiscible oils and hydrocarbon solvents or organic solvents in water. It has been widely acknowledged that selective filtration materials able to effectively separate immiscible oil organic solvents from water need to combine a macroporous structure, such as the structure of a mesh, of a membrane or fabric, and so on, with wettability selectivity, that is contemporaneous super hydrophobicity and super oleophilicity. Due to these features, these materials let oils or organic solvent flow through freely while repelling water completely. And the aim of our work has been to explore the utilization of our plasma process to modify the wetting properties of polymer meshes to obtain selective filtration materials for the separation of hydrocarbon liquids from water. Let me show just briefly some results. On the left, you can see the SEM images of a pristine polyethylene terephthalate mesh, while we have also below the images for a plasma-coated polyethylene terephthalate mesh. While on the right, you can appreciate that okay, there is a separation system. The mesh is in the middle of this system, and the transparent liquid is hexadecan, while the blue liquid is water dyed with methylene blue for better visualization. As you can appreciate, the plasma treated mesh does not separate hexadecan water mixture, because in the beaker here you have both liquids, you collect both liquids. But if we move to the plasma coated mesh, we can appreciate that it effectively separates hexadecan water mixture. And in fact, we have oil mixtures here, the oil here in the beaker, while water is does not pass through the mesh. A good separation efficiency was obtained with several hydrocarbon solvents and hydrocarbon mixtures. And we obtain a good recyclability of the plasma-coated mesh. That is, after 50 cycles of separation, the separation efficiency is greater than 99%, and also the advancing and receding contact angles are almost unchanged. So the superhydrophobicity is maintained. Let me move to the second part of this talk, dealing with the surface modification of complex porous materials, such as polymer foams. When we started this work, we really aimed at investigating the potential of a DBD for the surface modification of porous materials, that is, of both their outer and inner surfaces. And this is due to the fact that these materials are very have applications in various fields, such as water remediation, heterogeneous catalysis, and in the field of regenerative medicine, for instance. I will show you some examples on two possible applications, that is water remediation and heterogeneous catalysis today. For our work, since it was really a proof of concept study, we decided to select an open cell polyurethane foam with a porosity of 97%. And as you can see, appreciate from the SEM image on the left, this foam is really characterized by isotropic, fully interconnected network of ligaments and pores. So this was really a choice to select this kind of material to start our work. On the left, on the right, the typical carbon 1s6ps signal of the foam is reported. There is a main contribution from hydrocarbon, from the hydrocarbon component, and then some contribution from oxygen and nitrogen, containing functionalities. The first approach we used is the direct approach. That is, we located the foam inside the discharge region of a parallel plate DBD system with lateral gas injection into the system. And we really sandwiched the foam between the dielectric covered electrode of the DBD system, so that the feed mixture could be really obliged to flow through the material. By using this approach, we were able to obtain plasma ignition both outside the foam, but also throughout the entire three-dimensional porous structure of the foam. And this can led to an effective and uniform modification of both the outer and inner surfaces of the foam. To start, we first of all investigated the deposition of simple fluorocarbon coating by feeding the plasma with an helium and hexafluoropropene mixture. And this was not for applicative purposes, but really to very well distinguish in XPS analysis and so on, the coating from the substrate. And as you can see here, I reported the carbon 1s XPS signal of the plasma coated foam. In this case, the deposition time is 30 minutes. And as you can appreciate here, we have the typical contribution of CFX groups and the typical contributions that we observe in case of classical Teflon-like coatings deposited by hexafluoropropene in low pressure and atmospheric pressure plasma. The contribution from the hydrocarbon component that can be ascribed both to hydrocarbon, let's say, to adventitious carbon and to the coating and to the substrate is always very low. And also the chemical surface chemical composition is really very uniform. If we look at the surfaces directly exposed to the plasma, that is the left side, the right side, and also if we look at the cross-section of the foam. So in addition, we observed moderate change in surface chemical composition if after a deposition time of 5 minutes. This means that even if the deposition time is low, we could expect to have a conformal coating, let's say a uniform coverage of the complex material. Let me show some images from SEM analysis. First of all, the low magnification image shows that plasma ignition does not alter the morphology of the porous material, the polymeric porous material. And in other investigations, we also confirmed by a mechanical characterization that also the mechanical properties did not change after plasma treatment. But if we look at a cross-sectional ligament and we look at some parts of the different region of the ligament, we can really observe the presence of a thin layer within the foam. Let me just show you very briefly, mention another study we did, because just to explore the potential, because for instance, as you know, there are limitations in the gas gap thickness at atmospheric pressure. And at least we were able to treat, at least with the expertise we have in Bari on power supply, we were able to easily obtain the plasma, the helium, in within a 5 millimeter thick foam. We also explored another possible approach, that is the remote approach, in which you don't need to place the sample within the electrodes, but the sample is outside the plasma source in contact with the plasma that exits from a DBD plasma jet. As you can see here, we tried to to evaluate the possibility of depositing a water-stable coating containing carboxylic groups on a foam. In a first study, we investigated the deposition on a classical flat silicon glass substrate. And we tried to transfer this process to the foam. In this case, just to mention a little bit, the feed mixture, the plasma was fed with helium or argon again, and acrylic acid and ethylene. The co-deposition is really almost mandatory to obtain water-stable coatings containing carboxylic groups. When only acrylic acid is used, the water stability of the coating seems very compromised. So the first approach was to use, as you can see in the scheme of the source, here we use a simple cylindrical coaxial DBD system in which this is a cross-field jet in which the electric field is perpendicular to the flow field. So with this configuration, we just observe that the spreading of the plasma plume over the top surfaces, the top surface of the foam sample. You can obtain some deposition inside, but it's not so effective. For some applications, that can be interesting, but we would like to improve the deposition inside. And for instance, we utilize here very simple strategy. The keys, we use a sample holder that is a dielectric covered grounded metal plate. In this way, we obtain an enhancement of the plasma along the flow field direction. And even if it's not clear from the picture here, we were really able to obtain the plasma also inside the foam throughout the porous structure. And for instance, here you can see some SEM observation. We performed on the top of the sample, on the bottom surfaces of the sample, and also the interior of the sample, and we were able to obtain the coating also throughout the sample. This is just to mention how it's possible, since due to the versatility of the DBD design, it's possible really to try to act on this, to adapt the source and the process to the material and to the needs. I would just now focus on two possible applications we have explored so far. The first one relates again to the exploitation of the wetting properties that we are able to impart to our foams after plasma treatment. And in this case, I will show you some results regarding the preparation of absorbent materials for oil water separation. The principle is very similar to the one to the preparation of filtration materials. That is, selective solvents able to effectively separate oils and non-polar organic solvents from water need to combine a porous structure and large pore volume, such as in case of a foam, and wettability selectivity. In this way, we can be able to obtain materials that are able to selectively absorb the oils or organic solvents with high selectivity from water, while repelling water completely. And so the aim of our work has been the optimization of plasma processes able to modify the wetting properties of open cell polyurethane foam to obtain selective absorbents for the separation of hydrocarbon liquids from water. Let me focus on the wetting properties of the pristine foam. The pristine foam is super oleophilic, so it absorbs mineral oil quickly, while it is slightly hydrophobic. It presents a water contact angle of 100 degrees. In the application of the material, this is not enough to obtain really oil-water separation with high selectivity, and the surface modification of the foam is needed. We optimized a two-step plasma process in this case. That is, in the first step, we used an oxygen-fed DBD to achieve the etching and nanotexturing of the foam surfaces. And then in the second step, we coated the foam with the low surface energy hydrocarbon polymer by using a DBD fed with the ethylene. Again, also in this case, from the SEM images, you can appreciate that the two-step plasma process does not alter the porous structure of the foam. However, if we move to high magnification images, you can, it is possible to see that the plasma treated foam present nanotextured surfaces. And you can appreciate this nano nodule that, in combination with the low surface energy hydrocarbon polymer, and this is confirmed by XPS that show that the surface chemistry is now dominated by the hydrocarbon polymer, allow to obtaining super hydrophobic and super oleophilic behavior. That is, to obtain wettability selectivity. Now the contact angle for water is greater than 150 degrees, and okay, the foam still absorbs mineral oil quickly. So here, the absorption capacities of the pristine and plasma treated foams are reported for both water and various hydrocarbon solvents, hydrocarbon mixtures, also gasoline, diesel oil, motor oil. And as you can appreciate, the foam exhibit a high absorption capacity for hydrocarbon liquids before and after the plasma treatment. However, after the two-step plasma process, we observe a drastic reduction of the absorption capacity for water. And these absorption properties were maintained after immersion in acidic, basic, saturated salt solution of water, and so on. And we explored, for instance, the recyclability of the atmospheric pressure plasma treated foam. And we observed that after 50 repeated absorption-desorption cycles, the absorption capacities for mineral oil and water remain unchanged. And absorption, most importantly, the absorption capacity for water remains very low, and considerably lower than that of the pristine foam. And this is confirmed by XPS and SEM analysis. The surface composition is always dominated by the hydrocarbon polymer deposited by from ethylene, and surface nanotexturing is always present even after 50 absorption-desorption cycles with water and an hydrocarbon solvent. The last part of this talk deals with the possible combination of these two topics. That is, we explore the possibility of depositing nanocomposite coatings on open cell polymer foams, and why. We explored actually the possibility of depositing TiO2 containing coatings on macroporous supports for photocatalytic water treatment. This work has been carried out in collaboration with Françoise Massingel-Plantard in Promes. And we explored the possibility of immobilizing photocatalysts on the surfaces of a complex porous material. Over the last decades, photocatalyst immobilization attract, or in general, catalyst immobilization attract the interest due to the fact that it facilitates the separation and recovery of the photocatalyst from the treated medium, and also it can enable the operation of continuous flow photoreactors. It has been also shown that among various supports, three-dimensional macroporous supports such as open cell foams can be promising because they provide a large interface for reaction, superior light harnessing capability, and flow resistance. So we investigated the optimized plasma process for the immobilization of photocatalytic TiO2 containing thin films on open cell foams, always with the typical direct DBD treatment in a parallel plate DBD system. And we compared both conventional glass flat substrates and with the polyurethane foams, just to evaluate if there are some differences on the deposition and on the performances of the material. And just here, I just summarized some results from the plasma coated foam, in which you can appreciate the presence of the nanocomposite coating containing TiO2 nanoparticles also in the foam interior. And we investigated the photocatalytic activity of these materials using a recirculating batch photoreactor designed and realized by Guy Plantard in Pommes. And we investigated the photocatalytic degradation of methyl orange in recirculating continuous flow conditions. And here another view of the apparent kinetic constant for methyl orange degradation we obtained for our plasma coated glass slides and polyurethane foams are reported. Actually, the greater the apparent kinetic constant, the greater the photocatalytic activity of the material. So we observed that for both types of samples, by increasing the nanoparticles concentration in the starting, dispersion, and the deposition time, it is possible to obtain an increase of the apparent kinetic constant. But in general, with the foam, it is possible to achieve greater values of apparent kinetic constants. And there are also other parameters that could be explored to further increase the activity of the plasma coated foam. Again, what about the recyclability? Of course, we investigate, it's really complicated to obtain a really, let's say, eternal photocatalytic material. But in our case, it seems that the results are quite promising. For instance, we tested, we observed that the best performing plasma coated foam presents remarkable reusability and maintain good activity after prolonged operation. That is, after 20 cycles of use and 40 hours of operation, you can appreciate after 20 reaction runs that the nanoparticles are still present. And the collaboration with the Pommes really helped us to really evaluate and characterize the material after 20 reaction runs. Let me point out that in the literature, very often, many photocatalytic materials are reported, but very often the characterization of the material and the stability of the material is tested from 1 to 5 reaction cycles. So we were really able to understand if the coating is really able to withstand the reaction and what we can improve So let me move to the conclusion of this talk. And simply, I'd like to again mention that in our work, we really tried to focus on the opportunities offered by atmospheric pressure plasmas and on some specificity of atmospheric pressure plasmas, that is the compatibility with the unconventional thin film precursors and the possibility of obtaining plasma ignition within porous materials. And while mentioning this, what we in such a way were able to enlighten, I would like to present, just to mention some open challenges that of course are related to some process drawbacks. And so the preparation, as far as the preparation of nanocomposite coatings is concerned, we can conclude that this approach is able to really can help us to broaden the nature and type of constituents that could be combined in a nanocomposite thin film deposited by a plasma process. However, we have several challenges to face, and here, for instance, in Toulouse, I perfectly know that there are very, very interesting results on the possibility of using environmental friendly and safe by design strategies. It's very important to also improve the discharge optimization and improve the nanoparticle quality, the nanocomposite qualities in terms of agglomeration. And this is, however, this is really flexible. So it depends from the application. As for the surface modification of complex three-dimensional porous materials, actually it seems that atmospheric plasma offers the possibility of achieving a fine-tuning of the chemical composition of morphology of both the interior and the exterior of surfaces of porous materials. Really a fine nanotexturing that is not easily achieved with simple wet chemistry procedures, for instance, or let's say other gas phase techniques in which there is no penetration of plasma. It's not enough to achieve nanotexturing. However, there are some challenges. That is the possibility of improving the discharge generation conditions and to achieve environmental friendly strategies and reduce the gas cost, the cost of feed mixtures and so on. And in this sense, let me add you that I'm really very happy to be here to discuss with you about this, because I think that it would be really nice to join our different backgrounds to really improve our processes and open really new opportunities to the plasma. And with this I conclude, and I thank you very much for your attention.
Merci Fiorenza. On a du temps pour des questions. Alors, il peut y avoir des questions à distance où on essaiera de gérer avec les mains qui se lèveront sur Zoom ou dans la salle. Je savais que c'est Richard qui allait démarrer. Je sais pas pourquoi.
Thank you, Fiorenza, for the presentation. I was wondering what's happening for the coating along the discharge tail when you are injecting aerosol. Did you observe any gradients, any evolution of the film composition along the discharge tail? Because you are feeding on one side, there is a consumption of the different spaces. And did you observe any evolution of the looseness of the film composition or something like that?
To be honest, there are some conditions in which there is such evolution. But since we inject a high amount of dispersion and we use a pulsed mode, we tried to be able to have at least at the center, that is the at the center, we have the length of our electrode is 5 centimeters. That is in the middle, from the 2 centimeters in the middle, really, to have a uniform composition. In that case, we did not observe gradients, but really because we try soon to focus on a condition in which we could really obtain uniformity, also for the foam. So, but in principle, it's possible. With the discharge modulation and high flow rates, in which the plasma uses a very small amount of the dispersion, you are able to obtain uniformity. There are other drawbacks that you don't utilize all the precursor, but in such a way you can mitigate these problems on the surface.
And what about the post-discharge?
The post-discharge, yes, there is some collection in the post-discharge region. And typically, of course, you mainly deposit particles. In the post-discharge, you really observe a greater contribution of nanoparticles. Yes.
The question. You mentioned the addition on the sample is mainly controlled by the matrix, by the polymer matrix. What about the role of the nanoparticle on the addition? And there is some change, as mentioned by Richard, along your material, outside or inside?
So, in principle, what I can say is that, in principle, regarding the mechanical properties of these coatings, since they are very porous and the matrix is just an hydrocarbon coating, they are in principle very, very, very soft. It does not seem really that the presence of nanoparticles in the coating is really detrimental for the adhesion. The only fact is that if you make a peel test, for instance, you mainly remove the hybrid part, and at the end you just have the polymer that remains on the surface. So, of course, there are other metrics. We could try other matrices to improve the mechanical stability, that is organosilicon matrices, and so on, to improve this aspect.
And the amount of the nanoparticle in the matrix have changed a lot the adhesion or not?
But yes, that is in the sense, not the adhesion, really the mechanical properties, because and the adhesion of the entire coating. That is, if you look at this coating, the one in which you have, sorry. Okay, this one, the last one. In this case, you have a greater adhesion. Let's say at least when you have a high contribution for nanoparticles, you mainly peel off all the nanoparticles, and then you have just in this sense.
Okay.
In this sense.
Thank you.
You're right.
Can you say a little bit more about the transparency of this porous material for the flow? Because I imagine that it only works for a certain, the flow should be able to go through. The problems mentioned by Alicia will be worse inside the foam, I suppose. That we get consumption of species as the flow goes through the foam.
In principle, the porosity, the pores of these foams are pretty large. Yeah. And the T is in the range greater than 100, 200 microns and up to sometimes 1 millimeter, it depends. And the porosity is very high, 97%. So the plasma mainly see the gas. Okay. A huge space. The volume, the pore volume is high. In case of the foam, with the dimension of the samples we used, we did not observe really a consumption, but in principle, if you increase the dimension of the sample and so on, this can occur. Just to tell you that we, for instance, just to support this consideration, we performed some GCMS analysis of the exhaust to see the depletion of the organic precursors, and is always less than 5%. That is, you really are not using, you don't have really a depletion of the, with the flow rates we used of our dispersion, you don't have what you could have with plasma enhanced chemical vapor deposition with a few ccm, let's say, of a precursor. So in this sense, we did not observe so much this effect.
So you don't know what exactly are the constraints on this fold. The holes should always be bigger than something, or you didn't really experiment with different folds or different materials.
No. It's in that sense, it's very important to optimize the plasma source and the design and so on. Because
for the discharge to be able to penetrate everywhere, it only works for a certain.
Yes. To be honest, we work up to let's say from using foams from 30 to 60 pores per linear inch. With the 60 pores per linear inch, that is reducing to, I don't remember exactly, 100, 300 microns, the pore size, we were still able to observe the. But if we decrease the dimension of the pores of too much, for sure, we will have, it's difficult. Then you need to think to the thickness, to the gas injection, to really have a uniform, and then also the aerosol. It would be better to use a plasma enhanced chemical vapor deposition rather than nanoparticles that can really, you can have some obstructions, I don't know. So the limitation, for the moment, we did not really use pores less than 300, 200 microns. And then we always use a full interconnected porosity. Because if there is not a full interconnected porosity, you can have several non-uniformities.
On a une question de Jean-Paul Bousse.
Hello, yeah, so very nice talk. So just a question, so for both of these technologies like photocatalysis or for the separation membranes, what do you see would be the possible first applications where in the real world for this kind of technology, and what would need to be done in order for that to become a reality?
In such a way, regarding the in particular catalysis, there is some needs in, okay, I'm not really expert in the field, but when discussing with people working on catalysis, there is a need in microfluidic catalytic reactors, or in, let's say, recirculating reactors in which you need to fill the cell with a porous material. And in this sense, there can be some possibilities. Regarding the oil-water separation, in principle, there are many, this is really a discussion regarding the different kind of strategies used for remediation of oil-water separation. Mm-hmm. There are some small prototypes that can be used, but it depends from the application. Sometimes a different type of wettability, that is super oleophobic materials and super hydrophilic materials, can be more useful in filtration, and we could work on that with plasma. In this moment, I feel that the possible application in the catalyst immobilization could really, in some systems, could be really, really nice. Okay. Well, water separation is very general. Let's say it's just to understand also that the material is well recyclable. That is the durability of the treatment we are able to impart to the material by using a plasma technology, because this is a weak point sometimes of our technology. We deposit thin films, and very often the thin films, if they are not really durable, they do not withstand long-term operation.
Okay.
So this,
yeah, and I was thinking, you know, could you be useful for either like oil spills, you know, in the environment, and for
yes,
you know,
yes, yes.
cleaning up and this kind of stuff?
There are opportunities in this sense.
Yeah.
To be honest, there are some applications in the sea, in the ocean. I don't believe personally to that.
Okay.
I believe to a small wastewater treatment systems.
Okay.
This could be useful. But in general, I think this in general for all water separation with these methodologies, I'm not referring to plasma treated materials. In general, the idea of using this in open sea, okay, I'm not really my feeling is not so, but for most small systems, it could be small volumes, it could be.
Okay. Yeah, so maybe it's not, the durability would be an issue in that environment, I guess.
The durability is always an issue, for instance, in the field of in catalyst immobilization. Yeah. There are many things that can be considered. For instance, the composition, the thickness reduction during the reduction of the thickness of the material during operation, and so on. It's always an issue. But let's say to have a material that can really withstand prolonged operation is really interesting, because even, for instance, in our case, we use that in photocatalysis, an inorganic TiO2 coating. Why an organic layer? Why? An organic layer will be attacked during photocatalysis, yes, but it is easily processable, and the material withstands very well the process. There is no dissolution of the matrix, because you can imagine to use a polar matrix, CIOX, all these things. Will it be stable in water? Not during photocatalysis. Stable in water. And then what happens during operation? And then what happens in various reactions with radicals, oxygen species, and so on. So there is always a balance. So in such a way, it's nice to see that a so simple coating can, because then you really need the help of people that works on the application and on the chemical application to really look at your material and imagine what can be changed to improve the material in terms of applications.
Thank you.
You're welcome. Thank you so much for your question.
Est-ce qu'on a d'autres questions? Merci, Fiorenza.
Thank you to you.